Hello. In this video, I'm going to present an overview of the fault propagation and hazard reasoning process that we have developed as part of an NSF-funded research project. Let's begin. This research focuses on developing safer systems using design stage failure reasoning. We developed a verifiable research process to meet three objectives. We need to be able to identify from historic data the potential hazards a new system could face. Then, we need an approach to simulate a significant number of those failures in complex combinations. Finally, we need to identify if those failure scenarios should be of significant concern to the designers. Now let's look at this process in a little bit more detail. The first set of steps is to develop the system information available at the design stage. This includes preliminary hazard data, system representation specifically, a functional and component model, and behavior simulations based on qualitative descriptions of behavior. For this video, we present a simple two-wheeled rover robot to demonstrate these steps. We have an FMECA of component failures from other rover-like systems as a hazard database. For this system, we identified a few functions and 6 components: a battery, controller, motors, and wheels. The system can be simulated using qualitative descriptions of behavior in MATLAB Simulink. Specifically, we use Stateflow to describe discrete nominal and faulty behavior. We developed a few algorithms to search through the historic hazard data and build a set of testable failure scenarios, including single and multiple faults. For example, our system with 5 components, with 3 to 6 failure modes in each component, results in a total of 492 unique single and 2 fault scenarios. Additionally, we created an algorithm to automatically simulate those scenarios and collect the state of each function through each scenario. This forms the results that our reasoning methods will be exploring. The first filtering step applied to this data is to identify the fault propagation path and determine the final system state as a result of each failure scenario. For example, in one scenario, the supply function changes from healthy to degraded as a result. A few steps later, the 2 control functions change status to lost. This in turn affects other functions in the system. This results in a graph of the fault propagation path. The final state of the system is also recorded, and that will be converted into a graph in the next set of operations. Here's where we start to use more complex graph reasoning methods to identify the probability that a scenario is important to the designer, specifically if it looks similar to known hazardous states. We begin by converting the end state of the function into a graph, and then modify that graph to enable a similarity comparison. We identify subgraphs that tend to exist in known hazardous scenarios. We count up the frequency of those hazardous subgraphs that appear in each scenario, and finally, we identify the probability that that scenario is from a population of the known hazardous scenarios. Then present this to the designer as an expert in the system to identify if the scenario is hazardous, and use this information to identify future scenarios. Recall, we proposed a validated research approach. Our validation approach has been to utilize a system testbed to validate the simulated fault propagation path and the functional impact of the simulated fault scenarios. The outcomes of this project so far have been the development of a means of a function-based failure simulation from known hazard data, a graph-based approach to identifying fault propagation path and new hazard identification, and a set of experimental procedures and metrics for validating the fault propagation paths and the functional effects. Thank you for watching. To find out more about this project, follow the links in the video description below to find published papers, examples, and more related to this research effort.